Okay. Right, welcome. Thanks for coming back in again, because I see you were kicked out. Right, so what I really want to finish today is the CH3051, because we really need to get going on those reactions. Has anybody started the organic booklets already or not? So I see April is typing. Yep, and Caleb, you have. Oh, good. Okay. And do you find these lessons are helping you get through the booklets a bit faster? Or perhaps you're going a bit more slowly because I'm taking a bit longer in the lessons? Okay, so just while you're typing, I'm just going to carry on with this. Okay. Yep, okay. Great. So you're all both ahead. Good. Now, isomers. We looked last week at the constitutional isomers. So it's the same molecular formula, but the atoms are connected differently. So it may have been a C double bond C with an OH, or it may be a C double bond O, or something like that. So they connected differently. Right. Hi, Johnny. Okay. And you would need to know constitutional isomers for the internal on stereochemistry. But what I want to go now is the spectroscopy. My brain was moving ahead. What you don't need for spectroscopy are stereoisomers, but you do need to know it for the exams. So, stereoisomers, you already know from last year the geometric isomers. Now, what is needed for geometric isomers? Hi, Tasman. So what sort of thing do you need for geometric? For constitutional isomers, you needed the same molecular formula and the atoms connected differently. And for geometric, you need the same molecular formula, and you also need, now I'm going to be very specific, and you should be as well, the carbon-carbon double bond. So you could even just abbreviate it as, you know, CO, like that. See, my brain is just moving just too fast ahead for me. Did see that one? Okay. Because what I was going to say next is that, remember, you've got two different types of double bonds. You've got the carbonyl C double bond O as well as a C double bond C. So don't just say it needs a double bond, be specific which type of double bond. At level 2 you didn't do the carbonyl really, apart from carboxylic acid, so it wasn't as important. Okay, and so you need the same molecular formula, you need the carbon-carbon double bond, and there needs to be one more thing before you're going to get isomers, because not every alkene can form geometric isomers. And it's something to do with the groups on each of the carbon atoms. Right, so each carbon of that double bond needs two different groups. So if there's two hydrogens on one of those carbons or two methyl groups, it will not form geometric isomers. Optical isomers, okay, so Caleb, you've got two of the same things on each end, depending on how you view that. So each carbon of the double bond must have two different groups, but of course both carbons can have the same group. So both carbons can have a methyl each or a hydrogen each, but you can't have one of the carbons having both. Okay, good. So optical isomers, also known as enantiomers, we're going to look at now. And okay, so this was just a summary of the constitutional isomers. Remember, if you change your functional group, or the functional group varies in position, or so on, you can vary the length of the chain and add side chains, perhaps put the side chains in different positions. Those are all different ways you can make constitutional isomers. So that was just a revision. Okay, and sorry. Now we get to geometric isomers. So as I say, it's the same molecular formula, okay, but you've got a different geometric configuration because there's a different arrangement on either side of the double bond. So what I'm trying to show here, this is a haloalkane, so you can see it's only got single bonds, so it's an alkane with the green representing a halogen. So if I look at it end on, can you see this is, that one, and this one up here is that one up there. So if I look end on like that and I spin the double bond, can you see each time I'm going to get the same molecule? That bond can rotate. Single bonds can rotate, and we get back to the same substance. If I look at a double bond and I look along the double bond, it can't rotate because the way those bonds are formed makes it stuck in position. So they're very limited in position, so it can't actually rotate as it does with a single bond. If you carry on with chemistry, you learn about hybridization and you'll learn why. But that's the reason why we can get geometric isomers, because there's no rotation about the carbon-carbon double bond, and you should spell that out, for excellence. It's always spelling out the obvious. It may seem very obvious to you, but write it down. Okay, so we said carbon-carbon double bond, okay, be as specific as possible, and we've also said the two groups must be different. So use symbols in your answers. You don't have to spend a lot of time writing out words if necessary. You could simply just draw something like this and say A, B, C, D, where A is not the same as B and C is not the same as D. And that is telling you that the same thing as the sentence over here. The two groups in each carbon atom of the double bond must be different from each other. Okay, I can see Caleb is typing, so I'll just check once he's done that. So that is, if it's on the same side, it's cis. So same, cis, the same sound, same for cis. And you can also draw a C for cis. That's trans. You can't draw a C for trans. It's like crossing the bridge, you're going across. So we've got cis and we've got trans. So it's got the same molecular formula of C2H2Br2, but and they're connected in a way the same way. On each carbon we've got a hydrogen and bromine, but there is a different position in space. Yep, trans across. Cis, that comes from the Latin for same, for like this side. So trans is across the other side, cis is this side. Yeah, so it just comes from the Latin, both words, trans and cis. Okay, so what I'm trying to show here is a way to remember is just think of C for cis. So that may be a way. And John Lee is sister, to remember sister. The same side. Okay, the SS perhaps, yeah. So whatever makes you help think. So I'm not going to go into geometric isomers too much. Always just be aware that you could form geometric isomers when you do a reaction. So have a look and see, do I have two different groups on each carbon atom? And therefore, if I do, I can get geometric isomers. So if you're asked to write all the products of the reaction, you can write the cis isomer, the trans isomer, and so on. Now, optical isomers is also the same molecular formula, okay, the same connectivity. So on this carbon atom, I've got a round thing and a square thing and a red thing and a orange triangle all connected, and I have the same thing over here. This carbon has also got a hydrogen and a red thing and a triangle and a purple. So it's got the same connectivity, which was the same requirement that we had for geometric isomers. So that's why they're both stereoisomers. They're the same connection, but the way they're connected in space is a little bit different. And the way to see this is, are they superimposable or not? So if you take one and you put it on the other, will it match up? And we talk about chiral or chirality, and that comes from the Greek for hand, handedness. So if you place your hand on top of, so not next to like this, on top of each other, will they match? So I'm trying to show. Like, does my thumb match with my thumb, or are they on different sides? They're different. So I can't superimpose my one hand on top of the other hand and have them match up. So we say they are not superimposable. Your hands are mirror images of each other. So if you hold your hand up to a mirror, then you will see its mirror image, and so you will see actually the other optical isomer. So this is one isomer, and this is the other optical isomer. Because if I pick this one up and I try to plonk it on top of here, can you see the grey ones will match up, the red ones will match up, but the purple one will be on top of the orange, and this purple one will be on top of that orange, or underneath that orange. I can never, no matter how I spin that molecule around, I can never make them superimpose. So the only way I can change this isomer to that isomer is by breaking these two bonds and swapping them around. Because remember what the difference is between an isomer and the same compound? If by spinning it around or doing something, twisting things, if it's the same, it's the same molecule. If I have to break a bond to make the other compound, they are isomers. Okay, so here I've sort of tried to show that there's a square thing and it won't fit on the triangle, but the triangle will fit into the triangle. So you can't superimpose it. So conditions, you need an asymmetric molecule, okay? And what we look for is a carbon atom, which we call a chiral carbon, that handedness again. And a chiral carbon has got 4 different groups. So show that you have understood the concept and not just learnt it by stating what the different groups is. So can you see this carbon is a chiral carbon because it has got a bromine group, or chlorine, whatever it is, a methyl group, an alcohol group, and a hydrogen. So it's got 4 different groups. Well, let me do it like that. 4 different groups. So it's chiral. And the same thing here. So, so there's 4 different groups or 4 different atoms. Now, some students think of groups as being functional groups. It doesn't have to be functional groups. It's just a group, like methyl is a group. Okay, or OH is a group. I know OH is also a functional group, but it just has to be a group of atoms. It could be an ethyl group, or a methyl group, or a propyl group, or something like that, or a bromine, or NH2. Okay, and that carbon with the 4 different groups, that asymmetric carbon, is called a chiral carbon. And as I say, identify it. So if they say, why can this compound form enantiomers? Don't just say the molecule is asymmetric and has a chiral carbon with 4 different groups on it. You could have just learned that. So identify that. Say that C1 is the chiral carbon. So here, because this is the functional group, the main functional group, so this would be C1, that would be C2. So do you follow in terms of how you identify the carbon atoms? You follow the normal naming. Okay. And then we say the molecule is chiral, and we can talk about a chiral carbon. So chiral can apply in a number of places. The molecule can be chiral. The chiral carbon can be chiral. Okay, so that's not a chiral carbon, but this molecule is chiral. And this carbon is chiral. Okay. And you can see No matter how we try and spin it around, those two cannot superimpose. I mean, we've got more or less the bromines matched up and the OHs matched up, but we haven't got the methyls matched up. Okay, now, because enantiomers are so similar, they're pretty much identical. They're going to pack the same way, they're going to have the same sort of intermolecular forces of attraction. Their physical properties are going to be identical. They'll have the same boiling point, the same melting point, and so on. The same density, everything will be the same. Okay, so this is just, sorry, it's an enantiomer, they're mirror images. You can't superimpose them. And then this is the point I wanted. They have identical physical properties. The only way you can distinguish one from the other is that they have this particular thing where they can change the plane of polarized light. Now, do any of you have Polaroid sunglasses? So not just UV sunglasses, but Polaroid ones. Anybody? Do you have sunglasses? You do have sunglasses? Okay. Now, do you know if they're Polaroid or not? Okay, they are Polaroids. Your screen, whether it's your smartphone or your computer or your laptop, actually has fairly polarized light. It's just the way the molecules in the screen are arranged. They arranged in strips, so the light comes out in just one plane. So if you take your sunglasses and hold it in front of your screen and turn your sunglasses in front of your screen, you'll notice there's a place where all the light comes through, and then there's a place where no light comes through. Okay, so polarized light is light that can only go in one plane, and I think it's, so here's light that sends out signals in all directions. Okay, when it goes through a Polaroid lens, what happens? The crystals in that lens are all in one direction, so only the light that vibrates in that plane can get through. Any other light gets blocked and can't get through. So all this light comes here, gets stopped, except for the light that is in the same plane as all those crystals in the Polaroid. And when that goes through, it goes through a tube of a particular length. When you always quote, you know, if you were doing at university and studies and so on, and you were making compounds, you'd have to quote, it's normally 10 centimeter tube at a particular concentration, because depending on the concentration, the length of the tube, that light starts turning, and it'll turn more and more until it's at a different angle. So if it came in vertical, it's now at a different angle. So you have a Polaroid lens here, your tube in the middle, and then a detector. So this is the analyzer detector, and this is where you turn it to see where that angle the light has come through in. And that differs in enantiomers. So if one rotates it by 10 degrees to the right, the other enantiomer will rotate it by 10 degrees to the left. So they do it by the same amount from left to right. Okay. If you have a mixture of enantiomers, that can be done in a number of ways, Caleb. It could be, normally the easiest is actually to use natural products like enzymes and so on, because your body is very specific to a particular enantiomer. So take, for instance, thalidomide, you know, that caused all those issues with birth defects. One enantiomer is fine, the other enantiomer was not. So your body processed that bad enantiomer and caused the birth defects, but the other one, you know, didn't have any issues. So your enzymes, they all done so atoms have to be in a particular location, and it just ignores the other one. Another example of enantiomers which are very different is your spearmint and your, I think it's caraway. So caraway has got quite a, has anybody tasted caraway? It's got a sort of a spicy type of taste, like aniseed sort of thing, okay? And spearmint. They are exactly the same molecule, but they are different enantiomers. So the one has got a slight, rearrangement of the atoms, but otherwise they're connected identically. So your body is very tuned into having atoms in a particular place. And so if you want to make enantiomers, you normally often just use natural products in the lab, because otherwise the lab work as like the thalidomide case, when you manufactured it, it would just manufacture both enantiomers. Because, lab work, you have to actually use an enantiomer to make another enantiomer. Okay, right, so this is an example, and I'm just going to move this on to show that optical rotation. I've got two over here. So I said from 25. So so that's, I'm trying to show, with the blocking of the light. And now we're going to, can you see how it's blocked the light now? So one way it let it through, now it's dark. And I'm just waiting for them to put the chemical in there. So they're going to use glucose. So a lot of compounds, natural compounds, are optical isomers. And glucose is one of them. And you only get the one sort being produced. An example also as well that's being done, lactic acid. Lactic acid made in your muscles is a different, so just while can you see, this is the way the analyzer works. They see where the light comes through, and would be in a different position to what it was before they put the glucose in there. And the more concentrated the glucose solution, or the longer that tube, the more it would change. Okay, so you're just saying about lactic acid. You can get lactic acid from sour milk, you can get lactic acid made in your muscles, and you can get lactic acid made by bacteria, in your teeth, the breakdown products of sugars. So, and I do get confused which one's which, but in the one, you'll get one enantiomer, and the other one, it'll be the other enantiomer, and in one of those cases, it'll make both enantiomers equally. And that's what we call a racemic mixture. So just be aware of that. This is, sorry, I've got to go back. So if I just go, it shows you how to do this whole thing if you wanted to try it out. If you've got your 2 lots of Polaroid sunglasses, so from about there. So they've got there again your sugar solution, and they've got a Polaroid coming on one side, and because they've got a very concentrated, it actually is quite pretty. It shows all the different colors as well. So that's just for fun. As a chemist, you would only be looking at how much it's rotated the plane of light, but you can do fun things as well like this. And if you look at Sick Science on YouTube, they have a whole lot of little different experiments that you can do. Okay, so you can actually, if you've got a Polaroid lens or Polaroid sunglasses, you can do that yourself. Okay, now you've got to be able to draw enantiomers. So, and you have to draw them in 3D to show that connectivity. So the best way is there's 2 different methods, and you decide which one works. So you draw your carbon, your chiral carbon, and it's approximately 110 degrees. I know it's 109 degrees, but do it just approximate, okay? Then you want, because that's all in the plane of the paper, so remember it's tetrahedral, so you now want to have a bond coming out of the paper and a bond going into the paper. So at round about a smaller angle than that, so around about 95, you try and show a bond coming out of the paper by having a thin wedge over here, closest to the carbon, and the thick end of the wedge coming out. That's trying to show this bond coming out of the paper. Now the last bond you're trying to show into the paper, so make the thick end closest to the carbon and trying to show it like by perspective, getting smaller and smaller going away. So this one is getting bigger and bigger coming towards you, and that one's getting smaller and smaller going away. And it's round about 20 degrees. So it's often helpful if you just, sort of try and hold 3 pens up and you try and get this tetrahedral shape, and you can get an idea of, so I'm trying to see, where you could see your different angles. So just play around with that and see, okay, what does that look like? Okay, I see John Lee's typing there, but that is a way. If the examiner looks at it and can't see the 3D structure because your angles are really weird, you're not going to get excellence. You could still get, I think, up to merit with it, unless it's really bad. So normally, even for achieved, if you've shown the 4 different groups around that carbon, they'll still accept it no matter what your bond angles. You don't have to be absolutely exact. So please don't sit there with a protractor and try and measure your bond angles. As you can see, I've just sort of done it approximately 110 when it's supposed to be 109.5 or something. So just to get the general idea. Okay, and then it says, please, you must add the atoms. Don't leave any bond without an atom on each end, because that is a definite no-no for the exams. They'll mark it wrong, even for achieved level. Okay, now this is the other method. So you draw, instead of having 2 bonds in the plane of the paper, we're going to be looking at it. If you've got 4 pens handy, you can do this yourself. We're now looking at, I don't know if you can see that, getting twisted here, 2 pens coming out towards you and 2 pens going away from you. So, yeah, something like that. Okay, so those are 2 bonds coming towards you. So a thin end by the carbon, and it's coming out, so by perspective it's getting bigger. Okay, and then the hashed ones going away from you. So the thick ends closest to the carbon, and hopefully by the perspective disappearing. So that's also showing that tetrahedral shape. Okay, and then of course finally add the atoms. So that is often, I think, easier to draw because it's sort of more or less all 90 degrees, whereas the other one is not. I know in marking schemes they love showing the other one and they don't really show this one, but I know certainly at university we were taught this method, and I think it's the easiest one. You prefer method 1, and that's fine. Yep. Okay, now how, yes, April, you can use any one in the exam. Both are correct. Okay. So to draw the second isomer, when you've drawn one isomer, how do you draw the enantiomer? Because they'll always ask you, draw the two, this carbon is chiral. Why is it chiral? Well, why can it form enantiomers? Draw the enantiomers. Okay, it's always questions like that. So you just simply swap one pair of groups around. So say you swap the top and the bottom one around, so the bottom one goes in the top and the top one goes in the bottom, or you swap the left and the right. So actually I'm going to just go back up again. Sorry for this. So if you were trying to do this one, okay, Joe, what's an enantiomer? They're optical isomers, so you've got to have a carbon with 4 different groups on it. So if you've got a carbon with 4 different groups, by groups I mean one can be a hydrogen, one can be a methyl, one can be a NH2, and one can be an OH. They've just got to be 4 different atoms or 4 different groups of atoms. Okay, and that can form then enantiomers. So optical isomers and enantiomers are the same thing. They just must be different. Either the 4 groups must be different, yes. The moment you have two, if I've got two methyl groups or two hydrogens, I don't have a chiral carbon and it can't form an optical isomer. So if you were swapping, with this enantiomers, the easiest way is actually just to draw the mirror image. So most people, if they go this way, they'll just draw the mirror image. So I don't think I've actually shown it, so I'm just flicking through this again. I've only shown it on that first one, but you'll see in the booklet. So, is number 1 a chiral compound? Will it form optical isomers? So you've got to look there and you've got to look, do I have a carbon atom with 4 different groups? And you're correct, I don't have a carbon atom with 4 different groups. Okay, what about the second one? Do I have a carbon atom with 4 different groups? And then my next question will be, which one is the chiral carbon? So you've got to tell me, is it C1, C2, C3, or C4? So it's a good checking of naming your parent chain. From which end do I name it? C3 is the correct one. Okay, that one. Remember, the oxo dominates over the hydroxy, so this one has to get the lowest number, so that's carbon 1, carbon 2, carbon 3, carbon 4. Okay, number 3, is that chiral, and can you tell me the number of the carbon, if it is chiral or not? Yes, it is, because it's got 4 different groups, and it is C2. So it's got a methyl group, a chloride group, a hydrogen, and an ethyl. So remember, methyl is different to ethyl, so there are 2 different groups. Don't just think, oh, one's an alkyl group and the other one's an alkyl group. They're the same. It's not. They're 2 different groups. And the last one is that, can that one form enantiomers? Okay, and which carbon? Yep, and actually this way it doesn't matter. If you even counted incorrectly, it would have been C3, because that's C1 because of that chlorine on there. That's C2, that's C3. Okay, so it's got a chlorine, an ethyl, a hydrogen, and a chloroethyl. So the chloroethyl is a different group to an ethyl. So that will be a chiral molecule. It can form 2 enantiomers. Okay, I know Caleb and Johnny are typing, so I'll go back if needed. Okay, here I knew it was somewhere, was trying to show the mirror images. So if you're doing method 1, or sometimes if your cursor is in that little typing box, it shows up as though you're typing. So if you do method 1, the easiest way is just to do the mirror image, and so if the OH is here, the OH goes there. If the hydrogen's there, the hydrogen is there. Chlorine on top, and the methyl at the back. Okay. Caleb, the same thing for you. It looks as though you're typing if your cursor is active in that chat box. Okay, now, obviously, because I said you can do mirror images this way, this first one is a pair of enantiomers. Okay, because this on the right hand side is a mirror image on the left hand side. Now notice how I connect my atoms. It's really important, particularly for 3D, that the bonding line, so these wedges and so on, are between the bonding atoms. So here it's COH. Now do you notice I don't write OHC? Can you see it's HOC, because the O is bonded to the C, not the H. So if you had said OHC, because you saw, oh, it's OH there, so I'm going to make it OH here, you are saying the hydrogen is bonded to an oxygen and to a carbon, and that would be marked wrong. So be very careful that you count correctly. Another common error is when you've got like the CH2, CH3, then people will often say CH2 and make this CH3. You know, there's a CH2, CH3, making then this carbon here have 5 bonds, and the CH2 of the one that was over there have only 3. So just check that you've made it done it correctly. So the first one is the second one an optical isomers? So have a look. Have we just swapped one pair of groups, or are there mirror images? And yes, what we've swapped here is we've just swapped these two around. I tricked myself too. Okay, as I say, I do like doing trick questions because it just makes you think. And this time around, because I prepared these last year, I've tricked myself. Why is that not enantiomers? Is it chiral in the good, April? Yep, I have got two groups the same, so I do not have four different groups. Okay, so as I say, I do put in trick questions and I've really trapped myself there. So look carefully, okay, so that you don't fall into the same trap. Number 3. Are those enantiomers, or have I simply redrawn the same molecule? First look for the 4 different groups. Okay, so what have we done here? Those are the same. No, they're not the same. So what have we done? We've swapped a pair there. So we've just swapped one pair. We've swapped the nitrogen with the hydrogen. So we've swapped one pair, so those should be a pair of enantiomers. So it doesn't matter which pair you swap. I mean, I always say, these or those, but it could be a pair like that, or a pair like that, or those two. So you just have to swap one pair of groups. Yes, so you can swap any two. Okay, and then the last one, are those enantiomers? So you look, does it have 4 different groups on it? And have I swapped one pair or 2 pairs? So we've swapped one. We've only swapped the methyl and the hydrogen. So those would be enantiomers. Okay, now so we've looked then so far at naming compounds, drawing compounds, the functional groups. We've looked at things you need to know about the structure, like primary, secondary, tertiary. We've looked at things like branched and straight chain that you also need to know. We've looked at things like saturated compounds and unsaturated. Do you know how to spot it from the formula? And we've looked at isomers, the constitutional and the stereoisomers, which can be geometric or optical. So the last thing that you need to know, this is fairly similar to your 3.4 standard. Now you won't be asked in depth about polarity and so on. So we won't say explain why this is polar and blah 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 like you do in the 3.4, but you are expected to use that information. So you are expected to be able to look at it and say, that's pretty much non-polar, so it's going to have weak intermolecular forces, only the temporary dipoles, and so it'll have a low boiling point. So it's more using the information that you learned in the previous standard. So alkanes, that's just carbon hydrogens, and they're only singly bonded. So you don't have to explain all that to state. Yeah, it's more an application. So it'll be more on the case of, I've got all these compounds, how can I identify them? So you'd have to be able to recognize alkanes are non-polar, so they won't dissolve in water, for instance. You won't have to go in depth to explain why they don't dissolve in water, about energy of attractions formed and so on and so forth. That you do in the 3.4, but not the 3.5 standard. Okay, now what I've done is a dipole moment, so you get a general idea. Alkanes, I know you get branched and unbranched, and they aren't exactly 100% symmetrical, but they're considered to be non-polar because they've got such a small dipole, molecular dipole. So please don't go around in organic saying alkanes are polar. They're considered non-polar. In the 3.4 standard, you can say there is a slight difference because the molecule is not symmetrical, and so on and so forth. So if I have a molar mass of 58.1, the intermolecular forces not only the temporary ones. It's quite a low molar mass, and I've tried to always pick a similar molar mass so we don't have to worry about that. It's got quite a low melting point and quite a low boiling point, and it's not particularly soluble in water. So if you've got alkanes and you're trying to find a method of how to separate out alkanes from the others or identify it compared to others, alkanes, if you add water, they're going to just float on top of the water. Okay. And it's a gas because at a minus 120. Alkenes, would this also be a gas? Just based on what you know with the alkanes, it's a similar molar mass. It hasn't got a very big dipole moment. It'll also, it'll be very close. Yep, it's also a gas. Okay, and also going to be insoluble. So, oh, and I have made a mistake in my structure. What is my mistake? Five bonds on this carbon. It is so easy to do. All right, yep, or two H's on the second carbon. So easy to double check, because so often, you're just racing through and you're drawing your diagrams and you make a mistake. Okay, so that's a gas as well. Haloalkanes. Now, can you see the dipole moment has jumped from the 0.05, 0.35 to suddenly 2 point something? So it's quite a bit more polar. Okay, our molecular masses, I've tried to keep them similar, but of course we now also have those permanent dipole forces of attraction. For the organic, you don't have to go into detail about this. I think I do ask you in the 3051 just so that you apply your knowledge from 3.5 to make you understand it better, but in the exam you won't have to talk about this. So the melting points are still quite low, but they're higher than what we've had because we've got now that permanent dipole force of attraction. Would this be soluble in water? It actually won't be. It'll be slightly soluble. I know you're taught our polar substances will dissolve in water, but actually they don't necessarily. Water has got strong hydrogen bonds, and you've got to form similarly strong forces of attractions between the solvent and solute in order to break those strong hydrogen bonds. And although this is polar, it doesn't cut it. So you're going to find that this will actually just sink below water with a little bit dissolving. Okay, so it's what we call sparingly soluble. A little bit will dissolve, but not very much. And it's really because it can't form hydrogen bonds. Okay, so it's a gas, a liquid, depending on the temperature. At room temperature of 25, it'll be a gas, but if it gets cold, like now, the frosty mornings, it'll be a liquid. Okay, alcohols. What can you tell me about alcohols? Would this one be a liquid or a gas? A liquid. Okay, and that's because we now have got hydrogen bonding. So we've got a smaller dipole moment than the previous one, but we've now got the hydrogen bonding. And will it be soluble in water? Yep. Now, the longer this alkyl chain, the less soluble it becomes. So propanol is about the limit. Once butanol is sort of not mixing very well, and pentanol, which smells like smelly socks, is certainly not particularly soluble. Okay, but can you see the big jump in boiling point? Because of the hydrogen bonding. Okay, and miscible means it's soluble in all proportions between water and alcohol. Okay, so that's a liquid. Why is the dipole moment smaller? Yeah, because the other one was about 2.01. Good point, actually. Good point, because you'd think oxygen would be more electronegative. This one's got 3 carbons in a row, and the other one has got 2 carbons. And each CH3 or CH2 helps distribute electrons. So although this oxygen is sucking electron density away, this carbon is not as polar or not as stripped of electrons because of these pushing electrons towards it. So a good one to perhaps compare for polarity is the chloro, so chloropropane with the propanol. And you'd find then that the propanol, the propan-1-ol would have a bigger dipole than the other one. So April, does that make sense? It's really because we've got more carbons that are pushing electron density onto this carbon. Okay, amines. What do you think this one would be? Solid, liquid, or gas? Because I'm trying to give you a sense of applying your knowledge you learned in 3.5. So it's going to be a liquid. Yep, it'll actually be a liquid. Amides are pretty much the only ones that are going to be solids. Okay, the rest for short chains will be liquids. Because we don't tend to give you anything really longer than 4 or 5 carbons. Okay, so you've got all 3 types of things, so you can see the boiling point has increased, not as much as OH, okay, because your dipole moment has dropped, and but it does dissolve, and what's important, it dissolves to form a basic solution. You know amines are soluble, I hope, because if you think of ammonia, ammonia is a base. The nitrogen lone pair, nitrogen is very happy to donate its lone pair of electrons and grab a hydrogen from somewhere. Miscible means it's soluble in all proportions. So if I take 5% of the amine and 95% of water, it'll mix. If I've got 50-50, it'll mix. If I've got 75-25 proportions, it'll still mix. Some substances are only soluble in particular proportions, and therefore you won't call those miscible. Okay, and that's a liquid. Aldehydes. What can you tell me about this aldehyde? Is it going to be a gas, liquid, or solid? Liquid. Good. Okay, it's got quite a high dipole moment because of that carbonyl. Johnny, not necessarily which ones are miscible, because every compound is going to be slightly different. Remember, the longer the carbon chain, the less likely it's going to dissolve. So propanol will have a different solubility to butanol or pentanol. Okay, I'm just giving you like examples here. So if you've got a short chain alcohol or a short chain amine or a short chain aldehyde, they will be liquids unless it's only got, well, actually even all of those, even if it's only got 1 carbon, they'll be liquids and they'll dissolve in water. But when we start going to 4 is normally the borderline. When we start going to 5 carbons, then the alkyl part starts dominating and it'll be less soluble and so on. Okay, so this doesn't have hydrogen bonding because that H is not bonded onto the O, but water can hydrogen bond with it, so it is soluble in water. So although this one doesn't have hydrogen bonding, so it's got a lower boiling point, it is soluble in water, the short chain ones, and it's a liquid. Okay, 2.91, so it's that carbonyl, you know, all these methyl groups pushing onto there, so it's giving it a bigger polarity. Is this going to be a liquid? Yep, great. It's a liquid because it's got quite a polar molecule, and this is acetone, okay, propanone acetone, and it's miscible because it's a short chain, quite polar molecule that can form hydrogen bonds with water. Amide. Now this is the one that's different. Amides can form solids. Some of them would be liquids, the very short chain ones, but normally you can identify them because they tend to form solids. Have a look at that dipole moment. It's the only one you're going to find that's close to 4. All the others will be most probably under 3. So It's because, remember we talked about nitrogen being basic, it's got its lone pair, it can donate. Nitrogen can actually use its lone pair to feed into carbon and get a positive charge, and oxygen then grabs one of those and gets a negative charge. So you've got a negative and a positive, so you charge. So can you see that dipole moment? We've now not just gone from slightly negative to slightly positive, we've gone from a positive to a negative. So it's a, like, if you like, a full charge difference, and that gives it a yeah, it's one of the structures we can draw. So it's not actually truly ionic, okay, but it is one of the structures we can draw that represents this molecule, and all the structures sort of contribute to the overall picture. But we use it to try and explain this very high dipole moment. Okay, but yes, when we draw it, we show three. Well, because carbon can only have 4 bonds, remember, so we show only one bond going up to carbon, up to oxygen, with 3 lone pairs of electrons up there, and so it has a negative charge because it's not sharing one of those pairs anymore. And nitrogen is sharing its lone pair, so we have a double bond here with a positive charge in it, because the nitrogen now has got 4 bonds. And whenever you have nitrogen with 4 bonds, it's got a positive charge. Okay, so this is what I'm trying to show here when it does that. So I've got the yellows to try and show I've got a big dipole moment. Okay, and look at that boiling point, 221. So it's going to be a solid. So if you think of amides, just think of solids. I think that the methanamide is borderline, I think, but anything above that, in fact, that may even be a solid. So think of solids as being, for amides, and all the others tend to be liquids apart from your alkenes, alkynes. Volatile liquids are ones with fairly low boiling point. So if room temperature is around about 25 degrees, so any liquid that has, I mean, we don't really consider ethanol as being particularly volatile. So anything up to sort of 60 degrees, it means just on a hot day, a lot of it is going to evaporate pretty quickly. So volatile just means it's got a low boiling point and evaporates quite quickly. Okay, right, carboxylic acids. Is this a liquid or is it a, okay, there's a dipole moment, liquid or solid or gas? Liquid, okay, and you know that from vinegar, okay, there's the boiling point, so it is a liquid, and actually ethanol's a funny one. At lowish temperatures it actually becomes a solid. So yes, there's a melting point, 17 degrees. So if you had pure ethanoic acid, you'd find on cold mornings it would be beautifully crystalline, and then it would melt during the day, and then at night it would go beautifully crystalline again. And I'm sure there's some YouTube videos on that. Okay, right, we're nearly finished. Esters. Now, esters have a similar dipole moment to carboxylic acids, but much lower than amides, of course. What do you think esters would be? Would they be soluble in water or not? Okay, in fact, it's a bit of a trick question because there's only one ester that will dissolve, which actually happens to be this one. It's the one with the least number of carbons in. So methyl methanoate. This one will dissolve, but any other ester, if I had ethyl methanoate or methyl ethanoate, they just have too many alkyl parts to them and they won't dissolve. They'll float on top and they'll be slightly soluble. So I might have said, this one's soluble, but the other esters are not. Now, normally you're not given this ester. I've just, as I say, tried to keep the molar masses similar. So if in one of your things of identify the compound sort of thing, an ester, you would, if you did the solubility test by adding water, your ester would float on top. Okay, and it's a liquid. Right, and then your acyl chloride is got a similar dipole moment, okay, because the chlorines don't really like giving off any of its lone pairs, so it doesn't do what nitrogen does. And what do you think about its solubility? Yep, it's soluble. So it is also a liquid, and actually it is very, very reactive with water. If you had a pure acyl chloride and you opened the bottle, particularly on a humid day, you would just see it fuming away. Okay, so if you added water to this, you'd see that immediate reaction of bubbling, and you'd get HCl gas being formed. I mean, it'll also sort of, if you had sufficient water there, it'll dissolve in it. But if you only add bits of water to the pure acyl chloride at a time, there's nothing for the HCl gas to dissolve in, and so you'll get the gas bubbling out. So it is a liquid, and if you added water, particularly if you added quite a bit of water, it would form HCl solution. And what would that do to litmus paper? Okay, it's acidic, so it would turn any blue to red. Okay, so, and I think that's so as I say, the whole point of this standard is not to know whether it's got temporary force of attraction or permanent dipole or so on, but it's being able to use that knowledge and doing an identification sort of thing. So if it's a solid, it's probably an amide, unless it's a big molecule, like if you're given benzoic acid or something, that is a white solid. And you'd always be given the structure of a compound, you know, like I wouldn't expect you to know what benzoic acid is. I'd show you a structure. So the first thing you can look at is gas, liquid or solid, and for this applies to short chain only. If it's a gas, it's an alkane or alkene. Liquids are pretty much the rest apart from amide. Some of them, if it's very short, actually all of these would be liquids, but of course the longer the chain, if you've got very long ones, you could go to a solid. But I don't think I've ever seen an exam paper with that. So basically your flow chart would be put it in water. So you need to add the water to show litmus paper changes, because remember, litmus paper or phenolphthalein or universal indicator paper, they won't change color without water, because they change color according to the H plus concentration or OH minus concentration. So check whether it dissolves or doesn't dissolve. Okay, or the other ones if it explodes. It's not a big explosion, but you will see bubbles. Okay. If it sinks in water, it's probably a haloalkane, depending on its density. Okay, if it floats in water, it's probably the other substances. Now, I've got here aldehyde or ketone underlined, because remember, those are iffy. If they're very short chain, they will certainly dissolve. So, acetone dissolves. And methanol and propanol will dissolve. But if they go to like pentanol, they're less likely to dissolve. Okay. And then remember the tests you did at level 2, the bromine and the permanganate. And if that doesn't ring a bell, we do repeat that in the CH3052 booklet. Okay. If it dissolves, test it with litmus. And if it's blue, you've got an amine. If it turns red, it's a carboxylic acid. And of course, this one as well, you would check the acyl chloride to see if it turns red. So if you get lots of bubbles and it turns red, you've got the acyl chloride. Don't just say if it explodes, it's acyl chloride. Say that you're going to test it as well. And if it's unchanged, you've got the alcohol or the amide. But as I say, the amide you can normally cancel because it's the solid. And aldehydes or ketones can come in this area as well. Okay, and I think that's about it. And as I say, that you will do in the